Hello and welcome, everyone. We know that time is precious, and so we want to thank you for joining our webinar today, Achieve Smarter Data, Faster Research, Bigger Breakthroughs with Adam Jones, our resident HPC expert. Hey, Adam, you want to come on and join us?
Hello, Maria. How's it going?
Good. How are you doing today?
Doing wonderful, wonderful. Thank you.
Thank you so much for dedicating time to putting this presentation together and walking us through transforming your research HPC. So really quickly for our audience, we encourage you to ask questions. There is a chat window over here on the right. If you could put in your questions, we know that you have challenges in the workplace. Please ask your questions there, and we'll answer them either throughout the discussion or throughout the webinar, or at the end of the session. So I'll hand it over to Adam to get us started.
Right on, Maria. I appreciate it. Thank you so much.
Sure.
So today I'm going to go through a real fun topic for me, HPC. So we're going to talk about transforming research with HPC. So my name's Adam Jones, and I'm the product marketing manager over HPC at Vast, and have a deep experience, about 25 years in HPC with a focus on research and healthcare and life sciences. So one of the cool things about Vast, and one of the reasons I started here, is that it's a platform that really transforms HPC. Pretty much one of the most pivotal platform changes, I'd say, in the last 2 decades when it comes to HPC. So let's get started. All right. So HPC has been a pretty stagnant architecture for a very long time. We've all dealt with the same, nuances and limitations over the years. Predominantly, a lot of this discussion goes into the limitations or functional issues around conventional parallel file systems. So that's Lustre and GPFS. So in my day-to-day workings in HPC and research, I spent probably 30 to 50% of my time managing those parallel file systems. So, that really takes away from being able to innovate, and it takes away from, functionally getting the return on investment out of your HPC infrastructure, since, you have idle infrastructure, due to your parallel file system being down. So enter Vast. So Vast, like I said before, it was a company that I found out about probably about a year and a half ago, and just on the HPC front, I was absolutely blown away. And one of the things that we've done is be able to kind of bring HPC into its next chapter as far as evolution, and that brings AI with it as well. And the cornerstone of Vast is, we truly do put our customer base at the top of our priority list. So we, through Gartner, being named as a leader last year in file and object storage, and then also too recently getting a net promoter score of 84, we truly focus all of our customer needs and meeting those customer needs. So we're not just there with you for the storage piece or the HPC piece. We're there with you during all of your issues, your problems, and we work to resolution. So that's where, if you talk to, any of our customers, you'll hear them all say that, we pretty much have the best the best support they've ever experienced, in not just an HPC infrastructure, but in an HPC and AI infrastructure. And again, as I go through this, if anyone has any questions, any comments, please feel free. I'd like to keep it as light and informational as possible. Let me go on to the next one. Yeah. Oh, I just noticed. I sincerely apologize that I did not advance that slide. So we go back to HPC architecture from its very beginning. Well, not its very beginning, but let's go back to like 2003. Google produced a white paper that was a pretty transformational white paper across the industry. And basically, it's the Google FS, or file system, which is the basis for pretty much all storage over the last 2 decades. And that's really a direct attached shared nothing architecture. And it worked extremely well for many enterprise environments over the years, but as we'll get into, it has some scaling issues, especially as you go up and beyond certain points and scale a system that meets the needs of today's HPC and AI workloads, and that is also designed for specific technologies like NVMe, Flash, things of that nature. So kind of wanted to start off with that this is where we're coming from. We're coming from the the beginning of 20 years of direct attached shared nothing architecture, and we really needed a new type of architecture that flowed through for HPC and AI. So when you deal with a shared nothing architecture, basically the general gist of the architecture is, you have a set of CPUs, and underneath those CPUs, you have, disk array enclosures, or whether they be, traditional hard drives or flash drives, but they're sitting beneath those CPUs. Now, one of the problems with that is you scale, you get to a point where it doesn't matter what kind of IOPS or throughput you add based on your drives below that, those CPUs become the definitive bottleneck of that sub array. And then one of the main issues is as you grow this, especially for writes, you start to encounter a tremendous amount of east-west traffic, whether that be for RAID functionality, for system functionality, for rebuild functionality. A lot of that east-west traffic is flowing very fast, and it's very intensive on the actual storage array itself. So much so that as you get up in some of the larger systems, you're going to have more traffic internally east-west than you are actually client or host traffic coming in. So that presents a huge problem, especially for NVMe architectures, Flash, and then HPC and AI. So at VAST, let me go here. So VAST, we've created the VAST data platform, and it really comes from 4 disparate or distinct pillars. We have the data store, that's our traditional storage. But one of the things that we've done from the beginning is we approach it from a multi-protocol native approach. So what that means is we're able to do NFS, SMB, object, block, all through the same platform with no translational gateway and no latency. And as we'll kind of get into as we get into the presentation, you'll see what that means from, as far as when you move over to database and data engine, how we move data, how data doesn't have to be moved or translated because it sits in a native format. Then we go into database, and database is, it's as fast as a traditional database, but you can query from it like the fastest data warehouse. So that has a lot of distinct benefits, especially when it comes to being able to take data that's natively in the data store format and actually be able to run database functions on it. So we're able to do that natively. And then also too, we have data engine, which data engine allows you to run computation functions natively in the platform. So it could be triggers from Lambda, containers, things of that nature. And then underneath that, we have what's called the data space. And I'll get into all these in a little more detail, but the data space allows you to have a global unified namespace across the board, not just attached to a specific data center or location, but geographically dispersed. So we're able from cluster that's in location, continent 1 can access data over in continent 2 and vice versa. So that's a huge piece, especially in HPC research. And one of my favorite features of this, being able to access any data at any given time without having to copy it from HPC cluster to HPC cluster. And then, so this is a little wider view of the actual data platform. So like I said before, we have the data store, which allows us to do enterprise, NAS, block, and object storage right off the gate. And then we also have the ability, as of about a year and a half ago, we do GPU Direct from NVIDIA. So we're bringing the vast storage functionality closer inside of the GPUs to further increase functionality and performance. Then, as I said before, you go over into the database, and in database, it's as fast as a database, and it queries just the same as the fastest data warehouse. So we're able to ingest via Kafka, Python, and then perform native analysis with Python, Arrow, Dremio, and a whole bunch of product suites like that, all natively. And then when you get into data engine allows you to run functions that are, SQL, events, lambdas, containers. And in my particular research that I did in HPC, I was breaking down where I would do primary and secondary genomic analysis. So primary genomic analysis is where I swab you and I run the primary analysis to actually complete a complete genome or exome of a patient. And then after that, I need to complete what's called secondary analysis. And what secondary analysis is, I take all that raw data, which per person or patient is about 150 to 300 gig, and I need to do alignments and things like that to actually get it in a manageable format. Hence, that's where Docker containers come in. When those Docker containers come in, I'm able to fire those up and do alignments to where I'm breaking up that raw data into 23 chromosomes and all the specific genes in those chromosomes, and I can figure out the variant files or the variants of them to then start to do AI model training and inference and things like that to develop precision medicines. Before, I had to kind of, take pieces of it on my HP infrastructure, then go over to a Kubernetes infrastructure. With this, you could natively do those functions within Data Engine. So I could take, my process data that's sitting in Data Store and immediately have it go into containers that are sitting in Data Engine to do all those variant alignments to where I could do precision medicines for that particular patient. Oops, sorry. Okay, so this is kind of a high level overview of functionally how all this works, and it's a little bit different than other storage functionalities that you may be used to. And like I said, we started out as storage, but and it was particularly in HPC research storage, but it was always designed for AI from the beginning. So the way that this works is we have at the top layer, we have what's called C nodes. And these can either be a combination of multi-function servers, or they can be single-use servers. And I'll get into that on the one of the next slides. But inside of these, what we're running is we're running stateless containers. So these are running Docker containers that are sitting inside of there. And at any given time, any of these C nodes have access to all the specific storage that sits on those D nodes, which are the disk enclosures. So how that works is when you take any one of these C nodes, one C node is able to mount all of the storage that's associated with those D nodes. And what that gets you is if you lose a series of C nodes, you're not going to lose functionality to that specific data set. So we're allowing everything to see everything at any given time, all through an NVMe fabric, which natively is running InfiniBand or Ethernet. So we're very open and flexible about that. We have traditional HPC. A lot of individuals are using InfiniBand. Also, too, we have a mix that are using Ethernet, and then in the AI space, there's more on the Ethernet side. But really, like I said, we have these stateless containers that across the board are just connecting through an NVMe fabric and doing remote calls to that storage like it's attached locally. And what that gets us is complete flexibility of not having a rigid environment where if we have certain nodes fail, it impacts access. Now, if you lost almost all these nodes, you still would have access, but you would have at some certain point, you would have a reduced IOPS throughput count as you lost more of those, but you're still always going to have access even up to just having one C node. And one of the cool things that buys you is, there we go. One of the cool things that buys you is these clusters are completely asymmetric. So what that means is as you're building out new and as you're adding on to this cluster that you have, unlike traditional storage, we're not bound to a specific generation of hardware. So you can start out where you have a massive cluster that's sitting on generation one, C nodes and D nodes. And then, say a year down the road, or maybe it's even a few months down the road, and we've changed models and you want to expand that, you don't have to do some complex data migration or anything like that. All you do is take those new C nodes and those new D nodes, they plug into the exact same NVMe fabric that they were using before, and you're up and running. We have some customers that are using as many as 4 generations of hardware within a single cluster. So that asymmetric design of having those stateless containers allows you to be able to have, that flexibility of being able to grow a cluster and not have to have the typical administration and migration functions that you normally would have. And then this is a little bit more of a hardware-based view into what I was referring to. So at the very top of that, you have your C boxes. Now, C box it's going to have multiple C nodes that sit inside of it. Now, you can have a smaller, more simplistic version where you're just running one C node, which is a one-use server. But regardless whether you're running, a singular C node or a C box with C nodes, they're still going down and they're connecting to that fabric switch, which we were talking about, which runs InfiniBand or Ethernet. And then from there, it's going down into a D box, which has D nodes in it. That's where all of our flash sits. And like I said, it's a simple architecture. We've tried to keep it very simple. The main thing is that we're just using those stateless containers to really extract the identity and functionality, so where at any given time, any C node can mount every single bit of storage that's in that cluster. Sorry. Okay. So, what does this mean for HPC, and how does it impact HPC? So, one of the main pieces that I wrestled with within HPC is, like I said before, is around conventional parallel file systems. So, I had complex setups. I couldn't do online upgrades. I wrestled with, lack of uptime. Didn't have a global namespace. It was very difficult to manage. I lacked a lot of enterprise features, like snapshots and data recovery, things like that. I missed all those functionalities. They weren't present inside of an HPC infrastructure. And also too, I had lots of bottlenecks across the board. What this allows you to do is have a very simplistic HPC environment where you're no longer having to manage a parallel file system. So all of this is done over high speed NFS, and then we'll get into like how it does this in the element store, but it's just going to a native gate, not even a gateway. It's going to a native element store that in real time, regardless of the protocol, is placing that into that element store. And so what that means is you can have data going as NFS and it come out as objects. So this is really beneficial when you're talking about AI inference training and research, to where maybe you're doing computations, like you're doing protein folding in HPC, but then you want to be able to do AI workflows in there. On traditional systems, you have to take that output from your protein folding on the HPC side, copy it over into object storage, and then start to move on doing your training and whatnot. With this, it doesn't matter. It doesn't matter how it got put in or how it goes out. It's all the same. So you put it in as NFS, it's coming out as object, doing your inference training and things like that. So, like I said, it was built originally for HPC, but when we built this company, we were only like 2 weeks separated from when OpenAI became an entity. So AI has been completely the cornerstone of this architecture since we started. It was just we utilized it for HPC and predominantly HPC research from the beginning. And so as I was talking about with the element, And so as I was talking with the element store is just, it's a native element to where, whether you're running NFS, you're running RDMA, you're running SMB, S3, block, SQL, it doesn't matter. At any given time, that data, or specifically the rich metadata, is going to go down into what we call our storage class memory layer. And that's our high-speed layer that holds all this metadata and transactional data until it eventually sits down into lower tier, lower cost flash. So that's really the abstraction of that. As we have data going in and out at all times, it's being completely abstracted and put into this element store. So regardless of how you put it in or pull it out, it's all going to be the same mechanism with industry class, like lack of, there's no latency and delay. This is a complete, you ask for it in one protocol and you can get it in another protocol. And then what I was kind of alluding to earlier with data space. So again, data space is the ability to have geographically separated data sets, but being able to access them. So in HPC and research, like I said before, I'd run a computation on my HPC cluster, and say I wanted to share it with another university. Really, the only way that I had to do that was take that data and figure out some way over the wire to copy it. And a lot of my data sets sometimes could be in the tens to hundreds of petabytes. So it's not really a feasible thing to have to copy on demand just to be able to have to use it for a little while. And then also too, it's time to live. It expires pretty rapidly too, as more research is done to that data set. So what we allow is we allow top level metadata to synchronize across that storage class memory. We have we have remote locking, and we have remote read prefetch for speed. So inside of this, our engineers we've developed a lot of proprietary algorithms that do prefetching across the wire. So if you're doing one job and you put it in here, it starts to do prefetching, knowing that you're asking for something similar down the road. So you know across the globe, say for instance you're at one university in the United States and you have another university, say that it's in England, you're able in real time to access one another's data without any type of copying whatsoever. It's just native access, and it has complete ACL level control on it and things like that. But just as a whole, you're able to access any data from anywhere. And that's really probably one of the most, outside from me being able to get off conventional parallel file systems, being able to access any data from anywhere, that's a huge piece for me, like in research and life sciences. Uh-oh. All right. And one of the probably the coolest features of our actual the vast data platform is VMS, are the vast management server. So what we've done from the beginning, people are generally, if you're in an HPC environment, you're used to having to track things down, find it across the board, and really like a needle in a haystack. So when we designed VMS, it's an API first architecture. So it's Swagger based, deep in functionality. You can pretty much get this thing to do anything that you want. We also have the ability, if you have multiple clusters that are geographically separated, we can use what's called Vast Uplink, which is a centrally managed platform where you could see all of your clusters geographically at one given time. And then one of the things that we do as well is we have thousands of metrics in this thing. So you can dig down to any level fairly easy. And one of the cool things that I used it for, it's brand new, that came out in 5.3, is in HPC, a big piece. Say you run a job, or say you're running multiple jobs, and you have a researcher come to you and they're like, my job's running slow. What can you do? A lot of times that's a needle in a haystack, and I have to go down this route of trying to trace IO and where's this job go. We natively now have built into where you can have it's job observability. So you can find these jobs natively within these dashboards like we have on the screen here, and it'll show you that actual PID attached to that process, and you can track it all the way through the whole architecture down to the specific user. In a lot of cases when we've been using this, we found that our researchers ran duplicate jobs. But before that would have been very difficult to deduce just based on the architecture, the sheer size of it. So like I said, whether it be for HPC or AI, we try to make tools that are very easy to use and that are very intuitive and that give you the exact data that you need, that would have taken you hours or days to look for, off of competing products. Okay. So I've talked a lot. Oops, I'm gonna keep on doing this. So I've talked a lot, and probably the best thing for me to do is actually give customer stories. So one of the most common things that you'll hear our customers say is, a lot of times people were skeptical. How do I get off of this parallel file system that I've used forever? It's kind of like a dysfunctional relationship, and we've went through the cycles of explaining it, getting other customers involved. And one of the most common things you'll hear from all of our customers across the board is they'll say it just works. We have customers that will literally try to break the platform. And one of those instances at a research university is they didn't believe us that we had completely disruptive upgrades. So we had a complete upgrade going on the system. They tracked the IO to a specific C node, or where those stateless containers are, and actually unplugged the power out of it, and in real time rerouted the traffic, and their copy and their upgrade had no disruption. So we really like to put that in motion and really show that it's just not talk. We have some of the largest HPC environments in the world that are using this, and they're hitting it as hard as they can every day. Where if at 50% of that, their luster or their GPS environment would have broken down in some way. So our first example TAC, and TAC's probably one of my favorite examples. So TAC, which is the Texas Advanced Computing Center, they had a unique challenge of, they probably have 10,000 plus unique researcher and college attendees that are actually trying to use this cluster at any given time. And one of the main things for them is luster was really hurting their performance. A certain percentage of the cluster was either down. If they had to do upgrades, they'd have to shut the cluster down for a series of days or over the weekend. And it was just becoming one of those things where they needed to find a better solution. So that was the very beginning of TAC and VAST. So we were able to develop a solution for them that replaced their HPC infrastructure. And they just right off the bat had 30% faster computation on the storage side. And they found it to be 10 times more scalable. So this thing is, we have environments that are going up into the exascale on this. So it's a highly scalable infrastructure that still maintains the same performance. And that goes back down into the 100% uptime. So even during event failures, they were another customer that really tried to break the system. And even during doing computations and large data copies, even when we would do those upgrades, they never experienced any outage, any disruption. And a lot of that comes from, we don't have client software. So, unlike, Lustre at GPFS, where you have a huge infrastructure, lots of components, including client software, we don't have any of that. We just keep it as simple as possible using the fastest architecture in the back end. And one of the main features that's pretty cool is, along with getting HPC and AI functionality, you're going to get a lot of enterprise functionality in there. So based on the way that we do data reduction, some of our features, one of the features as far as, like let's think of like, data protection, ransomware, things like that, they're all natively built into the infrastructure. So right off the bat, TAC was able to get a 2-to-1 data reduction on their HPC environment. So not only did they get faster, have more reliability, more uptime, they also decreased their data footprint exponentially as well. And then the next one is Brown University. So Brown's a pretty cool one in the fact of, traditional HPC, but they wanted to be able to take their enterprise research and their HPC and have it off one platform. That was the minimum requirement of this, that it all had to be done on the same platform. So we were able to take the VAST data platform and have it to where it's doing HPC and it's handling their enterprise research along with other enterprise functions that are inherent within the university. And that all comes down to, like I said, those feature-rich functions, being able to secure PII data, audit logs, all the things that you would expect with enterprise architecture, but that maybe isn't present in HPC. We were able to deliver all that in real time. And the last one that's pretty cool as well is Seneca. So Seneca, this was a huge supercomputing example. For anyone that's not familiar, they have the largest. Well, they have the number 9 supercomputer on the top 500, Leonardo. And Leonardo and Galileo worked together within their distributed system. And what they wanted to do is they wanted to create a very large data lake, being able to have functionality of the storage functions that we spoke about previously and the database. So with database, we were able to create and manage, deploy across the board a 50 petabyte data lake that they are now using to connect Leonardo and Galileo together for their computation initiatives. So I've went through a little bit of HPC. I would love if anyone has any questions. If it involves your current HPC infrastructure or HPC into AI. I'd love to hear anything that you have. I understand that not the most exciting topic sometimes HPC, but as far as being able to take the antiquated versions of HPC and inject this in there, it's definitely a huge win, something that I've been passionate about, especially within research and life sciences. This is stuff that I'm personally working on to develop precision medicine therapies for cancer and other types of diseases. And pulling those limitations of conventional file systems really has allowed me to really expand my innovation, and that's all attributable to the vast data platform.
So Adam, we do have a couple of questions in the Q&A box over here on the right.
Okay, let me see here. I'm looking. Oh, I'm looking. I'm sorry.
I can read them for you if you'd like.
Oh, I see them right now. Okay, sorry.
Yeah, no,
Okay.
you're good.
I'll just go one by. So okay. What is the service running there?
You can read them for the audience because just in case they can't see it.
Okay. So the first one, let me read this. So on a compute node running an HPC job, what VAST service is running there? A container? What is the mount type? Does it require kernel modules? I'm trying to get a sense of what the deployed client looks like from an OS perspective point of view. So from HPC and AI, it's predominantly the same. You have these functions that are running in those upper containers on the C nodes. So those C nodes can also go into different types of nodes where you're running, extended amounts of GPUs to where you have more GPU, but they're running the same like on an HPC where you're using Slurm on your you're using Slurm like on your head nodes and your maintenance nodes, and there's no model, there's no kernel modification or like that. It's all just running through those nodes that are sitting on those C containers. Does that make you? And I'll just go through these. If you have any more questions. Okay, so the next one is, can you do contrast with Cumulo, Isilon, and Ceph? Just to point us in the right. Okay, so all of those architectures, especially like with Isilon and Ceph, those go back to, they are a shared nothing architecture. So as we scale those, especially as we get up into like hundreds of petabytes, they reach a particular limit based on the functionality or controller nodes that are looking at that underlying data. That's where we found, that's where those shared nothing architectures completely they scale out and they plateau at their max. So that's where we designed this shared everything architecture to where everything can see everything. If something needs more computation, you just give it more C nodes. You can completely scale C and D nodes, or computation and disk, completely disparate of one another. Still looking. Okay. Okay. So from Gavin, can we see some type of stats you can drill in on, like maybe IOs per second? Okay. So I'm trying to. Is there any way for anyone to connect with me, Maria? Is there like, what's the best? Oh, sorry, I think we can go. Sorry.
No, you're good. Connect with you. Yes, I can have. We can follow up after the session, and yeah, we can follow up with after the session.
Yeah.
Yes.
Because
I hope that's
Gavin on the.
Gavin.
Oh yeah. Oh yeah. Okay. So Annalise said. Okay. So if you click on the Q&A.
No, that's yeah. So yeah, we can connect with you and send you the answer separately.
Yeah. So Gavin, I'm working on a lot of HPC material now, all the way from introductory. I think in the next couple of days I'll have some white papers that come out where it's probably going to be rudimentary for somebody that's in HPC, but I'm starting from the beginning where I'm trying to explain HPC as a whole, and we'll get into performance metrics and things like that. That's something we're definitely working on. I don't know how much we completely have across the board. It just varies for specific HPC environments based on how many worker nodes they have and things like that. But I'm more than happy to discuss any of it or try to find any answers for you, or even as I'm doing performance analysis myself, I can put some of those use cases in there to actually come up with some of that output.
And then we just had one come in from Timothy Carroll.
Oh yeah.
At the top.
Okay. Apologies if you cover this up front, but are customers using VAST in hybrid on-prem cloud environments for HPC workloads? Great question, and I should have covered that. Thank you, Timothy. So one of the cool things about when I talk about like those C nodes and those D nodes, we are completely a software-based company. So irregardless of where the data sits, We don't care. So I like that. So I was paying attention. That's awesome. Um, so so we can run in any, so we can go up into AWS, Google, Azure. We also even have like hyperscalers. That we can like Core 42, Core Weave, all those. But basically, you can run any extension. So say that you're running at your primary research facility, you have your HPC system. At any given time, you can burst out, or you can have functionality that sits up in the cloud, and that same C node D node relationship with the vast management console, it's all the same. So we have the same user experience across the board. You can, and this is the same for HPC and AI. You can totally throttle those out into other environments, or you can have them permanently sitting where they're in other environments for for disaster recovery, for replication, things like that. So yeah, we can move into any cloud, hyperscaler, any of those situations.
Okay. Those were all the questions.
No problem, Timothy.
Awesome. Those are all the questions. Okay. Thank you so much, Adam, for presenting all of that wonderful information. And thank you, everybody who asked questions and also attended. If anybody wants to watch the session again, it'll be on our website. We appreciate everybody who attended. You may X out of the window once we're done here. So again, thank you, Adam, and thank you everybody for joining.
Thank
Have
you,
a
Maria.
beautiful rest of your day. Bye.
Have a wonderful day. Thank you.